Here's a really important series that comes up in a lot of examples when we're studying the convergence and divergence of series. This is the harmonic series. The sum, as n goes from 1 to infinity, of 1 over n. So let's write out the first few terms of this series just so we can get a handle on what it looks like. So when n is 1, we're going to have 1 over 1, which is 1. Plus the next term, when n is 2, we'll have 1 over 2, that's 1/2, plus 1/3, plus 1/4, plus 1/5, plus, and so on forever. This infinite sum. So a few things to note about this series. First of all, the terms are always positive. That's important to note. We've already seen some examples of series where the terms alternate back and forth, positive, negative, positive, negative. You could also have a series that doesn't alternate in a regular pattern, but in which still some of the terms are negative and some of the terms are positive. It turns out that understanding series whose terms are always positive and understanding how to tell when those series converge tells us a lot of information about the other cases. So it's good to note here, this is a series in which the terms are all positive. Also, the terms are decreasing. That is, 1/2 is less than 1, 1/3 is less than 1/2, 1/4 is less than 1/3, and so on. So a sub n plus 1, the next term, is always less than or equal to, but actually is always less than the previous term, an. For all values of n. Right? As our denominator increases, the denominator goes from 2 to 3 to 4 to 5 to 100 to 101 to 1,000,000 to 1,000,001, and so on. As the denominator gets bigger, the whole fraction gets smaller. So every term is smaller than the previous term that you added. Not only that, these terms are actually approaching 0. The limit of the sequence of terms is 0. In other words, the limit as n goes to infinity of just an. Well, that's the limit as n goes to infinity of 1 over n, which is, of course, as n gets bigger and bigger and bigger, 1 over n gets closer and closer and closer to 0. Now, that's not the same thing as the limit of the series. The limit of the sequence of terms means if you're walking and each term that you add is the length of the next step that you take, it means your steps are getting smaller and smaller and smaller. But you're still walking forward. You're still making progress and going forward and going further away from the starting point. So the limit of the series is something different. It certainly is not 0. It may have no limit at all. We don't know yet. If you've looked at the test for divergence in section 11.2, you'll know that in order for a series to converge at all, in order for a series to actually have a sum, it must be the case that the limit of the terms is 0. But the converse is not necessarily true. If a series has the limit of the terms equaling 0, the series itself might not converge. It depends on how quickly those terms go to 0, and that's why we have a number of different tests we're going to study in the next few weeks that will help us to distinguish which series converge and which ones diverge. So the fact that the limit of these terms is going to 0 doesn't tell us whether the series converges or diverges. let's try and draw a graph of this series, just so we can see what's going on here and get a visual representation. So our series is the sum as n goes from 1 to infinity of 1 over n. I'm first going to draw a graph of the individual terms. So on the horizontal axis here we'll have the n-axis, and along the vertical axis we'll have the value of the term. So the first term, when n is 1, our first term is 1. So we're going to go right up here. When n is 2, our next term is 1/2. That's right about here. So it's half as high as the original. When n is 3, our next term is a third. So I'll go about 1/3 of the way from... So I'm just going to estimate. It doesn't have to be exactly perfect. When n is 4, we're going to have 1/4, which is right here. When n is 5, we'll have a fifth. When n is 6, we'll have a sixth. Then 1/7, then 1/8, 1/9, 1/10, 1/11, and so on. Our terms always have a height of greater than 0, but they are getting smaller and smaller and approaching 0. And if we keep graphing this, if we keep moving off to the right, your little pieces are going to get closer and closer and closer to that horizontal axis. Now this is the graph of the individual terms. Now let's try and draw a graph of what the series looks like, what the partial sums look like as we add these terms. So the first partial sum is going to be just 1. It's just the height of that first term there. Next, we're going to take this second term of 1/2, and I just want to add it to the previous. So I'm going to stack it up on top of here. So let's see, how far do I go? That is about up to here. Right? This is 1, this is a half. Then I'm going to take this 1/3 and put it up here. That's going to be 1/3. Then I'll take 1/4 up here. There's 1/4. Then I'll take 1/5. Obviously, I'm running out of room here. We could try and shrink this. Now I've shrunk my graph a bit so I can actually draw more of it. And let's try and add in our 1/6. Here's 1/6. Here's 1/7, 1/8, 1/9, 1/10, and so on. Now, if you look at this, it kind of looks like, it gives the impression that maybe it is actually approaching some final sum that is a finite height here, which would indicate that this thing has a limit. But we shouldn't assume that. In fact, let's try and explore whether this series actually has a sum or not, whether it converges or diverges. So does the harmonic series converge or diverge? Let's write out that series again here. We have the sum, as n goes from 1 to infinity, of 1 over n. And I'm going to write out the first few terms. This equals 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. I'm going to write out quite a lot of terms, as many as I can actually fit on here, because it's going to be helpful to us. Plus 1/7 plus 1/8 plus 1/9 plus 1/10 plus 1/11 plus 1/12 plus, and so on. Now let's see if we can figure out whether this series converges or diverges. So here's what I'm going to note, is that here, this first term is 1. The next term is 1/2. Now, what if I look at the next two terms, 1/3 and 1/4? I'm not going to just repeat them. I'm going to note that 1/3 is greater than 1/4. And here I've got a 1/4 here. What if I lump those two together and add them? The sum of those two is 1/2 again. Let me look at the next four terms here. 1/5 plus a 6th plus a 7th plus an 8th. So 1/8 is 1/8. So 1/7, well, 7 is less than 8, but that means that 1/7 is actually greater than 1/8. So this is greater than 1/8. And 1/6 is also greater than 1/8. And 1/5 is also greater than 1/8. So we're actually adding up 4 copies of 1/8. That's 4/8, that's a half. So whatever we had in our actual series is greater than 1/2, those 4 terms. So what do we have? We have the first term was a 1, second term was a half. The next 2 terms together are greater than a half. The next 4 terms together are greater than a half. The next 8 terms will be 8 terms that are all greater than 1/16, which is again going to give us a half. Greater than 1/2. So if we go down the line here, if we add up all the terms in this series, if I add up enough terms each time, I can keep on adding a half, plus a half, plus a half, plus a half. However many 1/2s you want to add, you can find a point far enough down that series where you've added up enough terms to go beyond that. If you want to go beyond, if you want the sum to be greater than 1,000,000, well, 1,000,000 is 2,000,000 halves. So we just follow this process 2,000,000 times. Each time we'll have to double the number of terms that we're adding up to get a value that is greater than 1/2. But we can do that. There is no limit to the value of the partial sums here, because any value, no matter how large, that you want to achieve in your sum, you can add up enough terms to exceed that value. So this series is greater than 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2, etc., forever. Now, each of those 1/2s, it takes you longer to reach that point, because the first half we had to add 1 term. The next half we had to add 2 terms. The next half we had to add 4 terms. The next half we had to add 8 terms, and so on. So it will take you longer each time, but you can always get another half added on. And you can do that forever. And that sum is going to be infinite. Really, we shouldn't even say the sum is infinite, because an infinite sum doesn't really mean anything. Really, the series diverges. So the harmonic series is a classic example of a series in which the individual terms are approaching 0, but the overall sum goes to infinity. The overall series diverges. And you should keep this example in mind, because later on, as you're using the test for divergence, you're going to be very tempted when you see a series in which the terms are approaching 0. You're going to be tempted to want to say that that series must converge. But we know that there are series whose terms are approaching 0 that diverge, and the harmonic series is the classic example of that. There are many, many others out there.